When you look at this equation, what do you think it proves? Would you believe that it proves the Riemann hypothesis? Of course, it is very hard to believe that the proof of Riemann hypothesis can be achieved within 2 lines, and you are probably thinking, this is another typical attempt that is very likely to be wrong. However, within a few slides, I will demonstrate the proof, then I will give more detailed rigorous proof of each element, and finally at the end of this presentation, I will show you an astonishing straightforward verification technique that will dispel any remaining doubts that you may still harbor, and demonstrate that the proof of the Riemann hypothesis was in fact hidden in plain sight. Why is the proof of the Riemann hypothesis important? The proof of Riemann hypothesis would have a huge impact on understanding the nature of prime numbers, the Internet security, many theorems on cryptography and quantum physics. Hi. My name is Fayez Alhagan. I am a professor of electronics and computer engineering. Please note, this is a synthesized voice, and it is not my normal voice. The whole presentation is developed through automation, using LaTeX Beamer multimedia, text-to-speech, and PDF-to-movie conversion. In this seminar, I will take you on a fascinating journey of the Riemann hypothesis, to unveil an interesting relation between the sums and products that will serve as the basis of this proof. You do not need advanced mathematics to understand this proof. I will try to explain it in a simple and intuitive way that will be accessible to a wider audience. In this presentation I will show a concise proof of the Riemann hypothesis. As we know, the hypothesis is over 160 years old. There have been many unsuccessful attempts at proving the Riemann hypothesis. And I expect that also you have your doubts about this proof. Therefore, in the first section, within a few slides, I will demonstrate the proof, explaining the insight that makes it possible to have a concise proof within one slide. In the following sections, I will focus on clarifying the equations and their interrelations going back to the original historical sources. Focusing on the clarification of the principal zeros of zeta function, then, I will demonstrate a straightforward relation between sums and products, as well as the relation between the zeros and the poles of a function, which have surprisingly many applications. Culminating in the proof of the Riemann hypothesis and final conclusions. You can follow the progress of the slides at the top, and you can track the topics at the left bar. The link to my paper is below for further details. Here, I will give an overview of the proof within a few slides to set the stage. The Hadamard product of zeta over the non-trivial zeros is given by equation 1. Now, expanding the brackets, we have equation 2. Then, simplifying, we get equation 3. Finally, equation 1 is expanded as shown in equation 4. It is important to note the location of the principal zeros of zeta, shown in figure 1. Now, for the case where s is approaching in the limit the value 1, we have equation 5. With the well-known fact that in the limit s minus 1 times zeta approaches the value 1, and gamma half is equal to the root of pi. Therefore, equation 5 becomes as shown in equation 6. Now, since sigma, the real part, is located within the critical strip, that is, sigma is equal or greater than half, and is less than 1, which means that 2 sigma minus 1 is equal or greater than 0, and is less than 1. Therefore, equation 6 is true only when 2 sigma minus 1 is equal to 0, which implies that sigma must be equal to half for all the non-trivial zeros of zeta. This concludes the proof of the Riemann hypothesis that the real part of every non-trivial zero of the Riemann zeta function is sigma equal to half. Here, we have the proof in a concise form, as shown in the following equation. Basically, the first part of the equation is the Hadamard product of zeta, and the second part is the zero's location between half and 1 for the real part of the zero. taking the limit as s approaches 1, and combining these two parts, logically implies that 2 sigma minus 1 is equal to 0, and as a consequence sigma must be half. Probably, you still have some doubts, and very likely, you would pose several questions regarding this proof, such as, why is the Hadamard product of zeta over the non-trivial zeros is different from the literature, which is usually stated as in equation 10. With the usual statement, the infinite product is understood to be taken in an order which pairs each root, ρ, with the corresponding root, ρ minus 1. Also, you may ask, why is the term 1 minus ρ not included in the proof? For in the literature the non-trivial zeros of zeta are given as ρ and 1 minus ρ. Again, you may ask, why do you state that the zeros are located within the strip, half and 1, where in the literature it has been proven that the zeros are located in the critical strip, between 0 and 1. To answer these questions, I will start with a brief historical highlights, followed by clarifying the principles zeros and poles. Then, demonstrating the relations between sums and products, culminating in the proof of Riemann hypothesis. Starting with Bernard Riemann landmark paper published in 1859, entitled
Über die Anzahl der Primzahlen unter einer gegebenen Größe.
Here, he states his famous assertion, and also, note this little equation, that he stated without a proof. In his 1859 paper, entitled, On Prime Numbers Less Than a Given Magnitude, he writes, which translates to, one in fact finds about as many real roots within the limits, and it is very likely that all roots are real. Without doubt it would be desirable to have a rigorous proof of this proposition. And Riemann continues, however, I have left this research aside for the time being, after some quick unsuccessful attempts, because it appears to be unnecessary for the immediate goal of my study. Just beneath Riemann assertion, we find an equation for xi, see equation 11, that was stated by Riemann without a proof. This equation is in fact the product expansion for zeta, and was only proved 34 years later by Hadamard. Karl Weierstrass proved that an entire function can be expressed as a product over its zeros. Weierstrass's factorization theorem basically states that an entire function fz can be expressed as a product expansion over its zeros, as shown in equation 12, where Zn are the zeros of the function fz. Gösta Mittag-Leffler was a student of Karl Weierstrass. He proved that a function fz can be expressed as a sum over the function's poles. Mittag-Leffler's theorem states that fz can be expressed as an infinite series over its poles, given by equation 13, where r1, r2, r3, and so on, are the residues of fz, at the poles, a1, a2, a3, of fz. In a few slides, I will show later on, the relationship between the sums and the products. Jacques Hadamard published his paper in 1893, entitled
Étude sur les propriétés des fonctions entières et en particulier d'une fonction considérée par Riemann.
The translation, Study on the properties of entire functions, and in particular of a function, considered by Riemann. The paper was over 40 pages, which included the proof of zeta product, shown in equation 14. Before we start to develop the relations between the sums and products, first, we need to clarify the principal zeros and poles of a function. Understanding the principal zeros and poles of a function is essential to correctly formulate the function in terms of its zeros or its poles. There is a confusion when defining the zeros of a function. Consider, for example, the gamma function, which has the functional equation, shown in equation 15, from which we see that pi over gamma z has zeros at z equal to -m, with m equal to 0, 1, 2, 3 and so on. Whereas, from equation 16, we see that pi over gamma 1 minus z has zeros at z equal to 1 plus m. Now, the function pi over gamma z has never been assumed to have zeros at both z equal to -m, as well as at z equal to 1 plus m. This is because the principal zeros of a function are defined only with a pure z in the argument. Other variations of the argument, such as n-z or z plus n, are termed non-principal zeros. Here, we will look at the principal zeros of zeta. For the case of the Riemann zeta function, the symmetrical form of the functional equation is given by equation 17. We note that zeta has zeros at s equal to sm, s equal sm conjugate, and s equal to -2 m, with m equal to 1, 2, 3, and so on. It is worth noting that many people assume, from the functional equation 17, for zeta 1 minus s, that s equal to 1 minus sm, and s equal to 1 minus sm conjugate, are also zeros of zeta. Nevertheless, the principal zeros of zeta are determined only by using the pure argument s in zeta. Hence, the principal zeros are only at s equal to sm, s equal sm conjugate, and s equal to -2 m. Therefore, the sums and products of zeta should only be over the zeros s equal to sm, s equal sm conjugate, and s equal to -2 m, whenever appropriate. Contrary to the usual statement that the infinite product is understood to be taken in an order which pairs each root row with the corresponding root 1 minus row. Now, the locations of the non-trivial zeros are determined by considering the Euler product of zeta over the set of the prime numbers 2, 3, 5, p, m, so on, given by equation 18. Which shows that zeta does not have any zeros for real s greater than 1, and by the functional equation 19, no zeros for real s less than 0, save for the trivial zeros at s-2, m, due to the sign term. In 1896, Hadamard and Vallée-Poussin independently proved that there are no zeros on the line real s equal 1. In addition, considering the functional equation, and the fact that there are no zeros with a real part greater than 1, it follows that all non-trivial zeros must lie in the interior of the real critical strip between 0 and 1. Now, as can be seen from the opposite figure, it is important to note that the non-trivial principal zeros of zeta are located only in the real strip, with real s greater or equal to half, and less than 1, whereas the non-trivial zeros of zeta 1 minus s are located in the real strip, with real s greater than 0, and less or equal to half. Although this is a minor definition clarification, it is critical in proving the Riemann hypothesis. This has been overlooked, as 1 minus s m is equal to s m conjugate for all the known zeros. Thus, the product or sum over the zeros 1 minus s m is the same as the product or sum over s m conjugate for the first 10 trillion known zeros. I hope by now you are ready to dive into the relation between sums and products. Here, I will show the relationship between Mittag-Leffler's theorem and the Weierstrass factorization theorem within a few steps, that is, the relation between products and sums of a function. Please pay attention to the function definition. Relating the function small f to the function capital F, it contains some mathematical jargon, but basically states that a function fz, with the property that fz is equal to fb minus z, with fb equal to f0, and fz has simple zeros a, 1, a, 2, a, 3, and so on. Also, A reciprocal related function, fz, has simple poles, at the same zeros of fz, such that the residues of fz, at the poles, have the value r1 r2, r3, and so on. In summary, basically, the zeros of the function small f are the poles of the function capital F. Now, by Mittag-Leffler's theorem, fz can be expressed as an infinite series over its poles, as shown by equation 20. Also, based on the Weierstrass factorization theorem, Hadamard showed that an entire function fz has a canonical representation over its zeros, given by equation 21, where a, m are those same zeros of fz, with the condition that a, m not equal to 0, r is the order of the zero of fz at z equal to 0. P is a polynomial of degree q, and d is the smallest non-negative integer, such that the series in equation 22 converges. Now, consider the first case, the function fz equal f dash over f. Then, the residue, r m, at the simple pole, a m, of fz, is 1 for all m. Thus, by Mittag-Leffler's theorem, from equation 20, the function fz is given by equation 23. Integrating, we have equation 24, where the integration constant, c, is evaluated at z equals 0. Then, taking the antilog, we obtain equation 25. Here, we arrive at a Hadamard canonical representation of fz, with m equals 0 and d equal 1. Now, consider another case, the function fz equal f dash over f times z, which implies that f0 equal to 0. Then, the residue, r m, at the simple pole, a m of fz, is equal a m for all m. Therefore, by Mittag-Leffler's theorem, from equation 20, the function fz is given by equation 26, which simplifies to equation 27. Integrating, we have equation 28, where the integration constant, c, is evaluated at z0. Then, taking the antilog, we obtain equation 29. Finally, we arrive at another Hadamard canonical representation of fz. For the xi function, using Mittag-Leffler's theorem, to obtain the zeta Hadamard product over the principal zeros of zeta, the normalized function, in equation 30, is utilized. Noting that fs is an entire function with fs equal to f1 minus s, as well as f1 is equal f0 equal to 1, and it has principal zeros only at s, m, and s, m, conjugate. Taking the log, we obtain equation 31. Differentiating 31, we obtain equation 32. Here, we note that f dash over f has simple poles at the same zeros of xi, at s, m, and s, m, conjugate. Then, using Mittag-Leffler's theorem, for the sum over the poles of the function, and noting that all the residues are equal to 1. Thus, we obtain equation 33. Integrating equation 33, we obtain equation 34. Taking the antilog of equation 34, we finally obtain the Hadamard product, as shown in equation 35. Also, in a similar manner, we obtain another Hadamard product, as shown in equation 36. However, the Hadamard infinite product expansion is often stated in an abstract form as in equation 37, with the usual statement that the infinite product is understood to be taken in an order which pairs each root row with the corresponding root 1 minus row. Re-examining the assumption, which simply states that the infinite product is understood to be taken in an order which pairs each root row with the corresponding root 1 minus row. This assumption would give the expanded form shown in equation 38. Whereas, the rephrased version, with one word correction, states that the infinite product is understood to be taken in an order which pairs each root with the corresponding conjugate root, which gives equation 39. As you can see, from these two equations, just one word difference makes a world of difference. In an expanded form, equation 38 becomes as in equation 40, and equation 39 becomes as in equation 41. From which, we see that the two equations are equal only when sigma m is equal to half. However, if sigma m is not equal to half, then equation 40, as well as the statement that the infinite product is understood to be taken in an order which pairs each root row with the corresponding root 1 minus row, are incorrect. Therefore, the only correct form is equation 41. Finally, we are now ready to prove the hypothesis, since we have cleared all the issues concerning the zeros of zeta, as well as the product form of zeta function. Now, I will rephrase the hypothesis in a theorem that states the Riemann zeta function has only two independent sets of principal zeros, the set M and the set S. The set M of all principal trivial zeros of zeta lies on the real negative axis, with imaginary part t equal to 0, whereas the set S of all principal non-trivial zeros of zeta lies on the imaginary line, with real part sigma equal to half. The opposite figure shows the locations of the zeros. Riemann in his landmark paper 1859 showed that the zeta function satisfies the functional equation 42. Now, if zeta is 0, then from equation 42, either the sine and gamma part are 0, as in equation 43, or zeta 1 minus s is 0, as in equation 44. From which we see that equation 43 gives us the set M of all trivial zeros of zeta, that is, M contains the set -2, -4, -6, and so on. At the same time, equation 44 gives us another independent set, S of all non-trivial zeros of zeta, that is, S contains S1, S2, S3, and so on. Where S M is equal to sigma M plus minus I T M. Sigma is within the critical strip between half and 1, and I is the imaginary part. To determine the value of sigma, we consider equation 41 for the Hadamard product of zeta over the non-trivial zeros, as shown in equation 45. For s equal to 1, we have in the limit, when s approaches 1, s minus 1 times zeta approaches 1, and gamma half is equal to root pi, from which we obtain equation 46. Now, since sigma, the real part, is located within the critical strip between half and 1, it implies that 2 sigma minus 1 is equal or greater than 0, and less than 1. Therefore, equation 46 is true only when 2 sigma minus 1 is equal to 0, which implies that sigma is equal to half for all the non-trivial zeros of zeta. This concludes the proof of the Riemann hypothesis that the real part of every non-trivial zero of the Riemann zeta function is sigma equal half. To validate the result, with sigma m equal half, equation 45 can be restated as in equation 49. We see that the right-hand side of equation 49 is unchanged when we replace s by 1 minus s, obtaining the expressions for both zeta and xi with the argument 1 minus s, as shown by equation 50. From which we see that equation 49 and equation 50 are equal. This is also validated by the well-known xi functional equation of 51. Here, if any zero of zeta has sigma not equal to half in equation 45, it implies that xi s is not equal to xi 1 minus s, which would contradict equation 51. Therefore, all sigma m must be equal to half, which validates the proof. From this, we can hypothesize that the product form of the xi, with the original form shown in equation 52, developed by Riemann was very likely to have been the source of inspiration for the Riemann hypothesis. The conclusions. Proof of the Riemann hypothesis would unravel many of the mysteries surrounding the distribution of prime numbers, which are at the heart of all encryption systems. In addition, proof of the Riemann hypothesis would, as a consequence, prove many of the propositions known to be true under the Riemann hypothesis. The proof demonstrated here was based on a basic insight into the product expansion of the Riemann zeta function, as available from Hadamard's publication in 1893 and Riemann's publication in 1859, as well as clarifying that the product expansion is only over the principal non-trivial zeros of zeta. I would like to thank several eminent scientists and mathematicians for their feedback on the first draft and their encouragement, noting that any errors are my sole responsibility. Also, I would like to thank Bilal Asaf and Amra Okasha for final video and audio editing. Here is a list of the main references. Finally, I conclude with the concise proof of Riemann hypothesis in one slide. And I leave you to contemplate the fact that proof attempts have saturated the bandwidth, to the point it has become more challenging to prove that the proof is correct than to prove the hypothesis.